65 million years ago, a rock approximately 12 kilometers wide entered Earth's atmosphere at roughly 20 kilometers per second. It hit what is now the Yucatan Peninsula in Mexico. Within 24 hours, approximately 75% of all species on Earth were on their way to extinction. The dinosaurs, which had dominated this planet for 165 million years, were gone within decades of that single afternoon. The rock didn't care. It had no agenda, no malice, no warning system. It was just a rock, and there are millions more of them out there. This video is about what happens when one of the big ones finds us again. Not the flash, not the explosion. Everything that comes after. Before the clock starts, we need to be precise about what we mean by giant. Meteors hit Earth constantly. Right now, as you watch this, small rocks are burning up in the atmosphere. You've seen them as shooting stars. They're real. They happen thousands of times per day. They're harmless. The scale at which things get interesting, and by interesting I mean catastrophic, breaks down roughly like this. A rock 10 to 50 meters wide, the size of a house to the size of a city block, hits with the energy of a nuclear weapon. The Tunguska event in Siberia in 1908 was in this range. It flattened approximately 2,000 square kilometers of forest. If it had hit London or New York, it would have been a civilizational catastrophe. In Siberia, barely anyone noticed. A rock 100 to 500 meters wide, the size of a sports stadium to half a kilometer, hits with the energy of thousands to hundreds of thousands of nuclear weapons. It destroys a region. It causes global disruption, millions to tens of millions of deaths. A rock 1 to 5 kilometers wide. This is where we start talking about global climate effects. Massive tsunamis, fires across continents, temporary climate disruption, hundreds of millions to billions of deaths. And then there's 10 kilometers and above. This is the Chicxulub range, the dinosaur killer range. The range where we stop talking about casualties and start talking about extinction. For this video, we're using a 10 to 15 kilometer impactor, a rock roughly the size of Mount Everest tall, striking a continental landmass. Specifically, we're going to say it hits the central United States because that gives us the clearest picture of the cascade effects. This is not the most likely scenario. Rocks this large hit Earth roughly once every 100 million years. But they do hit. They have hit. And if one is coming, there is essentially nothing we can do about it. Here's what happens. The first question everyone asks is, would we see it coming? The answer is, maybe. And it depends on where it comes from. NASA's Planetary Defense Coordination Office and its network of survey telescopes have catalogued the majority of near-Earth objects above 1 kilometer in diameter. For those we know about, we'd have years, potentially decades, of warning. But there's a critical blind spot. Objects approaching from the direction of the sun are essentially invisible to ground-based telescopes until they clear the sun's glare, which, for a fast-moving impactor, might be days or weeks before impact. A 10-kilometer rock coming from the sun's direction could give us weeks of warning instead of years. And weeks is not enough time. The physics of deflection are straightforward in principle. You don't blow the rock up, because that just turns one big rock into millions of smaller ones, all still headed toward Earth. Instead, you nudge it, apply a small force years in advance, which becomes a large course change by the time it reaches Earth. The DART mission in 2022 proved this can work on a small scale. NASA crashed a spacecraft into a small asteroid moon and measurably changed its orbit. But DART hit a rock 160 meters wide. Our rock is 10,000 meters wide. The kinetic energy required to meaningfully deflect it, with weeks of warning, is beyond anything humanity has ever built or could build in the available time. Nuclear deflection, detonating nuclear weapons near the surface to ablate material and create thrust, is theoretically the most powerful tool available. But the planning, targeting, manufacturing of additional warheads and delivery logistics for a rock of this size, with weeks of warning, almost certainly doesn't work. The math is not in our favor. So let's say the warning comes. Weeks out, confirmed, undeflectable. What happens to civilization in those weeks? The short answer, civilization begins ending before the rock arrives. Financial markets don't wait for impact. The moment confirmation is public, every asset that assumes a future, stocks, bonds, real estate, futures contracts, currency, becomes conceptually worthless. Who repays a 30-year mortgage when there's no year 31? Markets crash, not in a panic, but in something stranger, a rational repricing of a future that no longer exists. The algorithms stop, the traders stop, the whole apparatus of global finance freezes because it has no framework for this input. Governments attempt to manage the disclosure. They fail. The information is too significant, too widely known in the scientific community, too visible in the data for anyone with a telescope to miss. The weeks before impact are a study in human nature at its extremes. Simultaneous mass violence, mass generosity, mass religious revival, mass denial, and mass grief. Every human response to death, scaled to 8 billion people simultaneously. But the real disaster doesn't begin when people learn about the impact. It begins when the asteroid arrives. The rock enters the atmosphere. This is where most people's mental model goes wrong. They imagine an explosion, a crater, a shockwave. What actually happens operates at a scale that makes those concepts almost meaningless. The rock is traveling at approximately 20 kilometers per second. That's 45,000 miles per hour. At this speed, the atmosphere cannot get out of the way fast enough. The air in front of the impactor compresses so rapidly that it superheats to temperatures exceeding 100,000 degrees Fahrenheit, roughly 6 times hotter than the surface of the sun. This compression happens so fast that the thermal pulse, a flash of radiation moving at the speed of light, races outward from the impact zone before the rock even hits. Everyone within approximately 1,500 kilometers who is outdoors and facing the impact site is exposed to this thermal pulse. At close range, it is instantly lethal. At the outer edge of this radius, it causes severe burns and permanent blindness. This happens in the seconds before impact. Before the rock touches ground, the killing has already begun across a zone larger than Western Europe. The rock hits at full velocity. It does not slow down meaningfully in the atmosphere. It is too large and too fast for atmospheric friction to matter. At the moment of impact, the kinetic energy released is approximately 100 teratons of TNT, roughly 1,000,000 times more powerful than every nuclear weapon on Earth detonated simultaneously. The word explosion doesn't quite capture it. The impactor and a significant volume of the surrounding crust are instantly converted to plasma, matter heated beyond the point where atoms can hold together in their normal configurations. A crater begins forming, not slowly. The crust behaves like a fluid at these energy levels. Rock flows like water in a pond. The crater that ultimately forms is approximately 150 to 200 kilometers wide and 30 to 40 kilometers deep, punching through the crust entirely in places. The states of Kansas, Oklahoma, and significant portions of neighboring states cease to exist as geographic features in their current form within approximately 2 minutes. The impact transfers energy into the Earth's crust as a seismic wave of unprecedented magnitude. We measure earthquakes on the Richter scale. The largest earthquake ever recorded was magnitude 9.5. The seismic energy from this impact is equivalent to approximately magnitude 11 to 12, a number so far beyond recorded experience that the scale loses practical meaning. This seismic wave propagates through the Earth at several kilometers per second. Every fault line on the planet is triggered simultaneously. Every volcanic system is destabilized. Within 30 minutes of impact, every major fault system on Earth has experienced its largest rupture in recorded history. The San Andreas, the Cascadia subduction zone, the Anatolian fault, the faults beneath the Himalayas, all firing at once within half an hour of each other. Major cities that survived the thermal pulse, Los Angeles, San Francisco, Tokyo, Istanbul, Kathmandu, are destroyed by earthquake within the hour. The seismic energy transmitted into the ocean floors generates tsunamis of extraordinary scale from every oceanic fault simultaneously. The waves that reach coastlines are not the 10 to 30 meter tsunamis of ordinary geological events. They are 100 to 300 meters tall as a 30-story building, moving at the speed of a jet aircraft. Every coastline on Earth is hit within hours. The timing depends on distance from the triggered faults, but no coast is spared. Miami, London, Tokyo, Mumbai, Sydney, Shanghai, New York. Every coastal city on the planet is inundated within 6 to 12 hours of impact. The majority of Earth's population lives within 100 kilometers of a coastline. Let's step back and look at the planet 24 hours after impact. The impact site is unrecognizable. Where the central United States existed, there is a glowing crater of still partially molten rock, surrounded by hundreds of kilometers of terrain buried under ejecta deposits hundreds of meters deep. When the impactor converted the surface rock to plasma, it didn't stay in place. The energy of the impact blasted material, pulverized and vaporized rock, impactor material, everything, upward at velocities that sent significant portions of it into orbit and beyond. This material is now coming back down. Imagine standing anywhere in the northern hemisphere, 30 minutes after impact. The sky, previously blue or clouded, is now streaked with re-entering fragments, thousands of pieces of superheated rock, ranging from dust to boulder-sized chunks, each one glowing as it re-enters the atmosphere. These fragments heat the upper atmosphere as they decelerate, raising surface temperatures across the entire hemisphere, not locally, not regionally, globally, simultaneously. In the hours following impact, surface temperatures across significant portions of the northern hemisphere spike dramatically as this thermal energy transfers from the atmosphere to the surface. Forests ignite, not because fire spreads from tree to tree. There's no time for that. They ignite simultaneously across millions of square kilometers as the thermal radiation from re-entry reaches the surface. The northern hemisphere, by evening of the first day, is experiencing continent-scale firestorms. The southern hemisphere has more time before these effects reach it. perhaps 12 to 24 hours of relative normalcy following the shockwave and tsunami arrivals. But the global atmospheric effects that are now beginning will reach it within days. What survival looks like at hour 24. The people who survive the first 24 hours are those who were underground, subway systems, mines, deep basements, purpose-built bunkers. The surface in the affected hemisphere is largely non-survivable for the first day due to thermal effects, falling debris and fire in the southern hemisphere, inland and elevated, away from the tsunamis, with some insulation from the worst of the immediate thermal effects. These survivors are physically intact, but looking at a horizon that glows orange-red in every direction and a sky increasingly thick with debris. At sea, far from coastlines. Ships in the open ocean survive the initial effects if far enough from the epicenter. The open ocean doesn't burn, and the tsunami passes beneath deep water vessels as a barely perceptible swell. These survivors are intact but isolated, watching coastlines they cannot approach. The Meteor impact is not just a very large explosion. The atmosphere changes, the sky closes. The explosion kills millions, hundreds of millions if we're being precise. But hundreds of millions is not extinction. The human species has 8 billion members. Even catastrophic immediate casualties leave billions of survivors. What converts a catastrophic impact into a potential extinction event is what happens to the atmosphere in the days, weeks, and months that follow. The dust and soot. The impact has blasted an enormous quantity of pulverized rock, fine particles nanometer to micrometer scale, into the upper atmosphere. The global firestorms are simultaneously injecting black carbon soot from burning forests, cities, and organic matter into the stratosphere. Unlike the nuclear winter scenario, where the soot comes from burning cities, this event is burning entire continents of forest simultaneously. The quantity of material entering the stratosphere is orders of magnitude larger. Stratospheric particles don't fall out quickly. They're too high for weather systems to wash them down. They persist for years to decades, circling the globe continuously, absorbing and reflecting incoming sunlight. Within weeks of the impact, measurable dimming begins globally. By month 2, sunlight reaching the surface has dropped to a fraction of normal, not 70 or 80% reduction as in a nuclear winter, but potentially 95 to 99% reduction in the most severe models. What does 99% sunlight reduction look like? Midday looks like deep twilight, permanently. Noon and midnight become nearly indistinguishable. Plants cannot photosynthesize at these light levels, not struggling, not producing reduced yields, cannot function. The biochemistry of photosynthesis has minimum light requirements, and what reaches the surface falls below those requirements. The temperature collapse. Without sunlight, the surface loses its primary heat source. Global average temperatures begin falling within weeks. The rate of cooling is rapid, far faster than seasonal changes, fast enough that it registers as an acute event rather than a gradual shift. Within 3 to 6 months, global average temperatures have dropped by an estimated 15 to 30 degrees Celsius. The tropics, which were 30 degrees, are hovering near or below freezing. The temperate zones are experiencing temperatures associated with the Arctic. The poles become so cold that they are essentially incompatible with any surface life that was previously living there. This is not a winter. Winters end. This is a new equilibrium, a stable cold state that will persist for as long as the stratospheric particles remain aloft. And the particles remain for years to decades. The acid rain. The impact vaporized enormous quantities of sulfur-containing rock. The firestorms have released sulfur dioxide from burning organic matter. These compounds combine with atmospheric water vapor to form sulfuric acid aerosols. The rain that falls, where it falls at all, because the disrupted hydrological cycle also reduces precipitation, has a pH approaching that of vinegar. Acid rain strips leaves from surviving trees. It acidifies lakes and rivers. It makes surviving surface water sources increasingly toxic without treatment. The water cycle itself is compromised. Without solar energy driving evaporation, the entire engine of rainfall slows dramatically. Some regions experience the acid rain problem. Others experience severe drought. Neither is good. But even poisoned rain and endless drought are only symptoms. The true catastrophe begins when Earth's living systems can no longer sustain themselves. This is where the food chain dies. From the bottom up, here physics becomes biology, and biology becomes catastrophe. Photosynthesis is the foundation of virtually all life on Earth. Not metaphorically, literally. With almost no exceptions, every calorie consumed by every living thing on this planet traces back, through some chain of eating and being eaten, to a plant or photosynthetic microorganism that converted sunlight into chemical energy. Remove the sunlight. Remove the foundation. The ocean dies. First, phytoplankton, microscopic photosynthetic organisms in the ocean, produce approximately 50% of Earth's oxygen and form the absolute base of the marine food web. With sunlight reduced to near zero, phytoplankton begin dying within days to weeks. When phytoplankton die, zooplankton, the tiny animals that eat them, starve within weeks. Small fish, anchovies, sardines, herring, the vast schools that feed everything above them, starve within months. Larger fish, the tuna, the cod, the salmon, starve within months to a year. Marine mammals, seals, whales, dolphins, starve within a year. The ocean, which contains the most abundant food resource available to surviving humans, systematically empties from the bottom up within the first 1 to 2 years. Land follows. On land, the sequence is slightly slower but equally complete. Plants begin dying within weeks of the light reduction. Not all at once. Root systems can sustain plants briefly without photosynthesis, drawing on stored energy. But within 1 to 3 months, surface vegetation globally is dead or dying. Insects, the critical middle layer of virtually every land-based food web, lose their food sources and begin dying en masse within months. Herbivores, deer, rabbits, cattle, horses, all grazing animals, are starving by month 2 or 3. Without vegetation, there is no food. Their population collapses within 1 to 2 years. Predators, the wolves, the lions, the bears, the eagles, follow the herbivores with a lag of months. The livestock that represented humanity's most accessible food resource, the cattle, pigs, chickens that required constant feeding and management, even in good times, die within weeks to months of the supply chain collapse, regardless of human attempts to maintain them. The mushroom exception. This is the one genuinely important exception in the darkness scenario. Fungi do not photosynthesize. They consume organic matter, dead wood, dead plants, dead animals, in a world full of dead organic matter and no light. Fungi thrive. Mushrooms become, for surviving humans, one of the most critical food sources. They can be cultivated in complete darkness on wood, agricultural waste, and organic debris. They provide real nutritional value, proteins, carbohydrates, vitamins. This is not a solution to the food problem. It is a partial mitigation. Mushrooms alone cannot sustain 8 billion people, but for communities that understand cultivation, they provide a bridge. By the end of the first month, the question of who survives has largely been determined by geography and luck. Let's be honest about the numbers. The immediate impact zone, the central United States and areas within blast range, loses its population essentially entirely in the first hours. The firestorms in the Northern Hemisphere kill an enormous additional number. The tsunamis kill coastal populations globally. The immediate aftermath, cold, darkness, the failure of all support systems, kills the vast majority of the remaining population within the first 3 to 6 months. By year 1, honest models suggest global human population has declined from 8 billion to somewhere between 100 million and 1 billion. And that range reflects profound uncertainty about the severity and duration of the atmospheric effects. The survivors cluster in specific circumstances: underground communities, those who went deep enough, early enough, with enough stored food and some source of energy generation. Mines are the most important structures on Earth in this scenario. A deep mine with a generator, stored food, water access, and a sealed entrance is more valuable than any building on the surface. Geothermal regions, Iceland, New Zealand, parts of East Africa, the Yellowstone region, ironically, parts of Japan and the Philippines. Geothermal heat is independent of sunlight. Geothermal energy can power lights, heating, and eventually indoor growing. Communities in these regions have an enormous survival advantage. Deep ocean vessels, submarines, particularly nuclear-powered submarines with months of independent operational capability, are effectively immune to the surface catastrophe. A nuclear submarine has power, water recycling, and limited food for its crew for months. The United States and Russian navies each have dozens of these vessels. The Southern Hemisphere interior, areas sufficiently inland to have escaped the tsunamis, with pre-existing food stores and the organizational capacity to manage rationing. The effects reach the Southern Hemisphere too, but with some additional time and temperature drops are somewhat less severe. For any surviving community, the arithmetic of food is unforgiving and has to be confronted immediately. A human being requires approximately 2,000 calories per day to function. Most stored food, canned goods, dry grains, preserved meat, contains roughly 100 to 400 calories per pound. A community of 100 people needs approximately 200,000 calories per day, roughly 1,000 to 2,000 pounds of stored food every single day, indefinitely. No community has that stored. Pre-impact food stores, even for the most prepared individuals, are measured in months, not years. The bridge to sustainable food production is the critical interval. Communities that can develop artificial light growing systems, fungal cultivation, insect farming, and geothermal greenhouse agriculture before their stored food runs out survive. Those that cannot, don't. This transition requires energy, some source of electricity to power grow lights, because nothing grows in the dark. Seeds, the genetic library of edible plants. The Svalbard Global Seed Vault in Norway, buried deep in permafrost, is one of the most important structures in human history in this scenario. Knowledge, how to set up and manage hydroponic systems, how to cultivate mushrooms, how to farm insects for protein, time, enough food to survive while the new systems are established. Of these, energy is the most critical constraint. A community with geothermal or nuclear power has a path. A community dependent on solar or surface-based energy has very nearly nothing. Let's talk about money. In a meteor impact scenario, unlike the slower collapse scenarios in this series, money doesn't get a runway. There is no period of inflation, no period of barter economy emerging from a degraded monetary system. Money simply stops being relevant, not over weeks or months, but within days of the impact. The reason is straightforward. Money is a claim on future goods and services. It has value because you can exchange it for something tomorrow. When tomorrow's physical reality is a world of darkness, burning surface and no supply chains, the claim becomes worthless. There is nothing to exchange it for. What replaces it is not barter in the traditional sense. In the immediate aftermath, what matters is calories. Stored food is the supreme currency. Everything else is priced in calories. A doctor's services, a mechanical repair, security. All of it is denominated in food, energy, electricity specifically. The community that can generate electricity can grow food under lights, can maintain medical equipment, can communicate, can produce heat. Energy generation capacity is the foundation of any surviving economy. Knowledge. Certain forms of practical knowledge become extraordinarily valuable. Agricultural science, medicine, electrical engineering, mechanical maintenance. A person who knows how to set up a hydroponic system or repair a diesel generator is worth more than a person with $1 million. Seeds. The genetic library. A seed vault becomes more valuable than a gold vault by orders of magnitude. Community structure. The ability to organize collective action, make binding decisions, and enforce them without state machinery. The communities that develop functional internal governance survive at dramatically higher rates than those that don't. What government looks like. National governments don't formally dissolve. They simply become irrelevant to the survival calculus of the communities making life and death decisions in real time. The President of the United States, in whatever bunker the continuity of government protocols delivered them to, has authority over a country whose surface is largely uninhabitable and whose population is concentrated in scattered underground and geothermal communities with no communication links to the federal government. Authority, in practical terms, flows to whoever is actually providing the calories, the warmth, and the security. This is the most local possible governance. The community leader, the shelter manager, the person who organized the food rationing. Over years, if communities survive, more complex governance structures re-emerge. But in the first year, government is whoever is keeping you alive. Let's move the clock forward. The immediate catastrophe, the impact, the fires, the tsunamis, the first freezing months, is in the past. What does year 2 look like? Year 5, the atmospheric clearing question. This is the variable that determines whether this is a catastrophe humanity recovers from or an extinction event. The stratospheric particles will eventually settle out. The question is, when? Volcanic sulfate aerosols, the particles from the supervolcano scenario, settle out in 3 to 7 years. That's terrible but survivable for a sufficiently prepared species. Impact dust and soot from continent-scale firestorms are more complex. The finest particles may remain aloft for decades. Some models suggest meaningful light recovery by year 5 to 10. Others suggest partial darkness persisting for 20 to 30 years. The difference between these outcomes is the difference between near extinction and extinction. If light recovers meaningfully by year 5 to 10, surviving communities that maintain seed banks and indoor growing capability can begin transitioning to surface agriculture. The planet re-greens. The food web begins rebuilding from surviving organisms. Human population stabilizes and begins recovering. If darkness persists for 20 to 30 years, the energy requirements to sustain any human community through artificial means for that duration are essentially beyond what scattered survivors can maintain. The population decline continues until it reaches a number that geothermal and nuclear-powered communities can sustain indefinitely. Perhaps millions of people globally, perhaps far fewer. In year 2, the surviving communities most likely to be functional are submarine populations. Nuclear submarines can operate for months on a single fuel load, but they eventually need resupply. Those that found safe harbors in geothermal regions or that rendezvoused with other surviving vessels form the nuclei of some of the most technically capable surviving communities. Geothermal settlements in Iceland, New Zealand, and East Africa. These communities have been building their capacity since impact. Iceland in particular, with its near-total geothermal energy dependency and small pre-impact population, is one of the best-positioned locations on Earth. By year 2, a functioning Icelandic community under artificial light, fed by geothermal greenhouse agriculture, is plausible. Deep mine communities, wherever fuel lasted and organization held, mine communities represent another survival node. They lack the renewable energy advantage of geothermal areas, but may have significant stored resources. Now, the oxygen question. Here is the aspect of this scenario that most people don't think about, and that makes the long-term picture genuinely uncertain. The atmosphere contains approximately 21% oxygen. Oxygen is continuously replenished by photosynthesis, by plants on land and phytoplankton in the ocean. If global photosynthesis drops to near zero for years to decades, oxygen is no longer being replenished at normal rates. The reservoir in the atmosphere is enormous. It would take thousands of years to meaningfully deplete at zero production. But it is not infinite, and in the context of a decades-long darkness scenario, the very long-term trajectory of atmospheric oxygen is a genuine concern. More immediately, the CO2 that photosynthesis normally removes from the atmosphere begins accumulating. Decomposing organic matter, the billions of tons of dead forest, dead marine life, dead organisms, releases CO2 as it breaks down. Without plants to absorb it, atmospheric CO2 rises. In enclosed spaces where surviving communities are living, bunkers, mines, sealed geothermal communities, CO2 management becomes a critical engineering challenge. But surviving the darkness is only half the story. Eventually, one question remains: what happens when the sun returns? Assume, for the purposes of this section, that the more optimistic models are correct, that meaningful light returns by year 7 to 10, that human communities, reduced to tens or hundreds of millions globally, survive the darkness through a combination of geothermal energy, underground agriculture, and brutal rationing. The sky clears. What is the world they emerge into? The ecosystem. The surface is not barren. Life is extraordinarily resilient at the microbial level. Bacteria, fungi, archaea, organisms that can survive on chemical energy rather than sunlight, have continued operating throughout the darkness. When light returns, they are the seed from which the ecosystem rebuilds. Pioneer species come first: mosses, lichens, certain ferns that can exploit low light levels. They colonize bare soil and rock surfaces, beginning the process of building organic material that more complex plants can root in. After pioneer plants come grasses and shrubs. After grasses and shrubs come trees. Eventually here means decades to centuries. The ecosystem that existed before the impact, the complex interconnected web of millions of species, does not return in human lifetimes. What returns first is a simpler world, tougher, less diverse, dominated by fast reproducing generalist species. The large mammals are largely gone. The megafauna, elephants, whales, large predators, require complex ecosystems to support them and are among the last to recover. If they recover at all, the mass extinction this impact causes is estimated to rival or exceed the Chicxulub extinction, potentially eliminating 50 to 75% of species on Earth during the darkness period. Evolution will fill the empty niches. Over millions of years, diversity will return. But the world that human survivors emerge into after the darkness is a biologically impoverished world, simpler, quieter, emptier than the one that existed before. Human civilization. The human survivors, tens to hundreds of millions of people, depending on scenario severity, are rebuilding from a very specific starting point. They have knowledge. The accumulated learning of human civilization is not destroyed. Books survived in bunkers. Digital archives on hardened storage media survived. The survivors know about antibiotics, about crop genetics, about electrical engineering, about medicine, about history. They have some tools, not the full industrial complex, that's gone, but hand tools, mechanical devices, salvageable equipment from the pre-impact world. They have seeds, ideally from the Svalbard Vault or from community seed banks established in the warning period. They do not have supply chains, industrial capacity, or large populations. The rebuilding is not a reset to zero. It is a reset to something like the early industrial era, with the advantage of modern knowledge applied to pre-industrial resource constraints. A community of 1,000 survivors with modern agricultural knowledge, a seed bank, basic tools, and a geothermal energy source is not starting from scratch. They are starting from a better position than any pre-modern civilization. They know what works, they know the science behind it. They don't need to rediscover antibiotics or germ theory or crop rotation. But they are rebuilding from a very small base. And the losses of the darkness period, the deaths of the specific people who held specific knowledge, the destruction of specific resources, create gaps that take generations to fill. Recovery to something resembling pre-industrial civilization, a world of towns, agriculture, trade, basic medicine, and written records, is plausible within 2 to 5 generations under optimistic assumptions. Recovery to something resembling modern civilization, industrial production, global trade, advanced medicine, digital technology, is a centuries to millennia project, if it happens at all in the form we'd recognize. Everything we've explored so far assumes one thing, that the asteroid actually strikes Earth. But before we end, we need to ask the question that matters most. How likely is that? And what are we doing to prevent it? We started this video with a number, 65 million years ago. Here's another number. There are currently approximately 2,000 known near-Earth asteroids larger than 1 kilometer in diameter. Of these, roughly 150 are classified as potentially hazardous, meaning their orbits bring them close enough to Earth to warrant monitoring. The 10-kilometer impactor in this video is not on that list. We would know if it were, but our survey is not complete. The population of smaller impactors, still large enough to cause regional to continental devastation, contains many objects we haven't found yet. And as we discussed, objects coming from the direction of the Sun are effectively invisible until they're close. The good news is that planetary defense is real, it's funded, and it works within limits. The DART mission proved we can move an asteroid. The international community has begun coordinating on detection and response frameworks. These are genuine, meaningful steps. The honest limitation is that they work best with time. Years of warning enables deflection. Decades of warning enables multiple redundant deflection attempts. Months of warning enables essentially nothing at planetary scale. The investment in early warning, in finding these objects years and decades before they become threats, is therefore the most important single thing humanity can do about this risk. Not for the planet. The planet will be fine. It has survived 5 mass extinctions and will survive more. For us, we are the first species in the 4 billion-year history of life on this planet that has the awareness to see this threat coming and the theoretical capability to do something about it. Every species before us, including the non-avian dinosaurs, had no warning, no understanding, and no agency. We have all 3. Whether we choose to use them is a policy decision, not a scientific one. And policy decisions are made by people, which means they're made by us. The rock doesn't care about our politics, our budgets, or our timelines. It never has.